As chemists started to understand the role that electrons played in chemical change, they began to realize that the most important electrons for chemistry were only the ones that were in the highest shell. So chemists began to look for ways that were simpler to describe only the important part of the electron structure of an atom. We're going to look at two of those methods today. One's called shorthand notation and the other one's called dot notation. So the most important electrons for chemistry are in the highest shell. Let's look at an example of an electron configuration and see if there isn't a reasonable way to shorten it. We'll use phosphorus. When we draw the electron configuration for phosphorus, this is what we have. 1s2, 2s2, 2p6. That gets us through the second row. Phosphorus is in the third row, so we'll go 3s2 to start with, and phosphorus is in the third column over in the p group, and so we end with 3p3. Now what chemists started to realize is here's the highest energy level right here, the highest shell. Only the ones that have 3 in front of them are from the highest shell, or what became called the valence shell. What came before that, well, that was the electron configuration notation for the noble gas that ended the previous row, which was neon. So for shorthand, what they did was they took the part of the electron configuration that encapsulated the noble gas that came before the element and put it in brackets. And then it followed up with only the part of the notation that comes from the current row, which for phosphorus is the 3s2, 3p3 part. So there's the shorthand notation for phosphorus. It's quicker to write. Another example is lead. When we did the electron configuration for lead, we had a pretty long list. It was 1s2, 2s2, 2p6. Third row is 3s2, 3p6. Fourth row is 4s2, 3d10, 4p6. The fifth row is 5s2, 4d10, 5p6. Lead was in the sixth row. So we start the sixth row with 6s2, then we had to go to 4f14, then 5d10, and then finally back up to 6p, and lead was the second element in the 6p block. Now to do shorthand notation, we have to go back and find the most recent noble gas. Well, noble gases all end in p6, so if we go back and look for the last p6, it's right there. So that's the part we're going to cut out and replace it with brackets for the noble gas that comes before lead. Well, this is 5p6, so we look for the fifth noble gas, and the fifth noble gas is xenon. So we'll put xenon in brackets, and then we'll just write this part afterwards. 6s2, 4f14, 5d10, 6p2. Now there wouldn't be much of an advantage to using this notation if you had to write the whole thing out in the first place and then figure out what the noble gas was and then screen that out. But it turns out that you can actually get this part, you can actually figure this out in one quick step on the periodic table. And then you can write electron configuration notation using that pattern from the periodic table that we've learned before. So here's how it works. The first thing you want to do is locate the element on the periodic table. Then you go up to the previous row and then all the way to the right to find the previous noble gas and then put it in square brackets. And then starting after that gas, complete the electron configuration just like you normally would. Let's do an example. Here's arsenic. There's the location of arsenic right there. So what we're going to do to find the previous noble gas is we're going to go up and over to the right. So the noble gas we find here for arsenic is the noble gas in the third row, which is argon. So we'll start out arsenic shorthand notation by just putting square brackets with AR inside because that's the symbol for argon. Then after that, we're going to go through the fourth period until we get to where arsenic is. So that involves a 4s, a 3d, and then a 4p, but only up to 3. So we'll complete our shorthand notation by writing that stuff down. 4s2, 3d, 10, 4p, 3. Try one. Give the shorthand notation for carbon. Well, let's locate carbon first of all. Carbon is element number 6, and it's right there in the periodic table. That's carbon. So to find the previous noble gas, we go up a row and then over to the right. And there we find helium. So we're going to start out our shorthand notation by writing helium and enclosing it in square brackets. Then, after helium, we start the second row. Second row has an S block of 2 there, so we write 2S2. And then we're into the P block, and we go 2 steps in, so 2P2 is how we finish that out. Try the shorthand notation for strontium. I'll give you the answer in a bit. Well, we need to locate strontium first. There it is. There's strontium. To find the previous noble gas, I go up a row and then all the way over to the right. And the noble gas that I find there is krypton. So for strontium shorthand notation, I'm going to start out with krypton in brackets. Then, starting with the 5th row, I only have to go to there. That's where I stop. This is the S2 column, and it's row 5, so I go 5S2. There's the electron configuration shorthand notation. Try gallium. Well, gallium is right below aluminum, right there. That's the location of gallium, and that's my target. To find the previous noble gas, I go up and over to the right. It's the 3rd noble gas, and that's argon. So in square brackets, I start out by writing argon. Since argon ends the 3rd row, I'm going to start with the 4th row to get to gallium. So I go through 4S all the way through, so 4S2, 3D all the way through, so 3D10, and then I stop 1 step into the 4Ps. So 4P1 is how I end the shorthand notation for gallium. Well, there was an even simpler way yet, because one of the things that we see is that shorthand notation often includes electrons that are not in the highest shell. Let me give you a couple of examples. We just did gallium. Germanium is the very next element. And so it's argon, 4s2, 3d10, 4p2. Iodine is down a row from that. So it starts out with krypton, and then the tail of this is 5s2, 4d10, 5p5. Or bismuth. Bismuth's noble gas is xenon, and then it follows up with 6s2, because it's in the 6th row, 4f14, 5d10, and 6p3. And then tin is krypton, kind of like iodine, it's in the same row, 5s2, 4d10, and 5p2. Now, if we look closely at these shorthand notations, we notice that for germanium, we have something that's not in the highest shell in that shorthand notation. For iodine, 4d10 doesn't belong in the highest shell, but it still has to be in the shorthand notation. For bismuth, we have 4Fs and 5Ds that are not 6s. And for tin, the highest shell is 5, and we have 4 D10s. So it'd be good to have a way to just even make this simpler yet. Here's how dot notation works. We give the element symbol. That's the first thing we do. The element symbol is given, so we'd write down like Ge for germanium or Ga for gallium. And then we surround it with dots. Every dot represents an electron, but they're only the electrons that are in the highest shell, or what we call valence electrons, electrons that are in the highest shell. Now, one of the things that we notice that if we're doing a lot of these things is that in the electron configuration notation, or even in the shorthand notation, the only sublevels that have the highest shell number are the S's and the P's. And S orbitals can contain 2 electrons, and P sublevels have 3 orbitals, so that's 6 electrons. So we will never have more than 8 dots in any dot notation. So this is a way of thinking about it. So imagine this is a generic symbol for an element, like C for carbon or N for nitrogen. If I imagine a sort of a square around this thing, I have 4 sides. And since I have a maximum of 8 dots, I'm going to think about 8 possible locations where I can put those dots, 2 on each side. Now, here's a habit that I'd like you to start getting into. And this isn't just arbitrary. This will really help when we start drawing symbols for for compounds. Put only one dot on a side before you start doubling up. So this is what I always do just to keep myself consistent. I put my first dot there, my second dot on the other side. On the top I put my third dot, and the fourth dot goes down below. Then I start doubling up and I just repeat the pattern. Dot 5 there, dot 6 there, dot 7 there, and dot 8 back down on the bottom. In that way you'll always build a dot notation that's helpful when you start drawing and predicting compounds. So let's do dot notation for iodine. If I look at the shorthand notation for krypton, here's what I find. I have 4d10, which I can get out of there, and then the highest shell things are just 5s. I have 2 in the 5s, and I have 5 in the 5p, so that's a total of 7. So I'm going to draw iodine symbol, just an I, and then I'm going to put in my 7 dots. So following my pattern, right, left, top, bottom, that's 4, then right, left, top again gets me to 7. Now I still have one missing location for a dot. That's okay. That's actually going to help me predict what's going to happen with iodine when it forms compounds. Here's bismuth. Highest energy level is 6. 4F is in a lower level. 5D is a lower shell as well. And so 6P, 3, and 6S2 are all the electrons that we have in the highest shell. 3 and 2 is 5, so I'm going to have 5 dots around bismuth symbol. So bismuth, Bi, would have 1, 2, 3, 4. Remember, I'm putting 1 on a side before I begin doubling up, and then the 5th dot is going to go there. Tin. Highest shell is 5. 4 Ds don't belong in that shell. If I take the 2 S's and the 2 P's and put them together, I have a total of 4 dots. So I'll put tin symbol down, 1 dot on the right, 1 on the left, 1 top, 1 bottom. There's my 4 dots. Now if you had to draw out the electron configuration notation, or even the shorthand notation to figure this out, it would be a kind of a pain. But it turns out that this is super easy to do. There's a very easy pattern in the periodic table. Lithium shorthand notation is helium and then 2s1. Below that is sodium. Sodium is 1 row down, so its shorthand notation starts with the next noble gas, which is neon, and it ends in 3s1. Below that is potassium. Potassium is argon, and then 4s1. They all end with only 1 dot in their shell, highest shell. So that means lithium will have 1 dot in its dot notation, so will sodium, and so will potassium. In fact, everything in that column will. And if we move over to the second column, we find that these all end in S2, and so they're all going to have 2 dots. So beryllium will have 2 dots, magnesium will have 2 dots, calcium will have 2 dots, strontium will have 2 dots, they'll all have 2 dots. We're going to have to skip over these things, but you can start to see the pattern developing. First column, 1 dot. Second column, 2 dots. If we make aluminum's column the third group, that group all has 3 dots, and then it's going to be 4, and then it's going to be 5, and then it's going to be 6, and then it's 7, and then it's 8. So whatever column number it's in, that's how many dots. Very easy to do. So you try these. Give it dot notations for hydrogen, carbon, and silicon. Well, hydrogen's in the first column, so 1 dot. Carbon's in the 4th column, so 4 dots. Remember, 1 on each side before we begin to double up. Silicon, right below carbon. Same column, so same number of dots. 1, 2, 3, 4. Try these. Nitrogen in the 5th column, so 1, 2, 3, 4. And after my 4 sides have 1 electron, I double up right there. Calcium, 2nd column. That's only 2 dots. 1 on the left, 1 on the right. Rubidium is in the 1st column. Single dot. That's very easy, and that's good because that's the notation that's the most helpful for us in chemistry. And we can write them out really quickly, and it helps us make predictions about what sorts of compounds are going to be formed by these elements.